All right, so welcome to my series of videos on statistics. And in this particular video, I'm going to teach you on estimating or estimation and hypothesis testing for two population parameters. Up until now, what we have been dealing with is that we have been dealing with estimation and hypothesis testing for a single population parameter. So if you remember, we have gone through doing a confidence interval for the point estimate of a mean, and then doing a confidence interval for the point estimate of a proportion. Then afterwards, we did hypothesis testing for mean, and we have also gone through hypothesis testing for a proportion. Now, by way of revision, remember that for any confidence interval, the formula for any form of confidence interval is that we need a point estimate. So here, what you must remember is that for any kind of confidence interval, is equal to the point estimate plus or minus the critical value times the standard error. So if you remember, when we are constructing the point interval, the confidence interval for the mean, when the population standard deviation is known, if you remember, we said that it will be equal to the sample mean, which is the point estimate, plus or minus the z value, where the z value is the critical value, and then the standard error is population standard deviation divided by square root of n. And remember that if you want, so this critical value here corresponds with a certain confidence level, but for the purpose of hypothesis testing, if you want to compute the critical value yourself, remember that z is equal to sample mean minus population mean all over the standard error, all right? So that is the formula for the z. That is, it is done when we are doing hypothesis testing. Now, if you want to compute the confidence interval for the mean when population standard deviation is unknown, okay, it is a sample mean plus or minus the t, all right, times the standard error. Now, the standard error, we will use the sample standard deviation divided by the square root of n, all right? Then for the purpose of hypothesis testing, if you want to compute the t yourself to be the sample mean minus the population mean over the standard error, which is the sample standard deviation with n, okay? Now, this means that for any critical value, if you want to compute any critical value, or the computed critical value is always the point estimate minus the population parameter divided by the standard error. The point estimate minus the population parameter divided by the standard error. That is the reason why, if you want to compute the z value of a mean when the population standard deviation is known, that z value will be equal to the point estimate, that is the sample mean, minus the population parameter, that's the population mean, over the standard error, all right? Then when the standard deviation is unknown, the T will be equal to the point estimate, which is the sample mean, minus the population parameter, which is the population mean, over the standard error, which is down here. Now, if I want to compute the confidence interval for a proportion, remember the generic formula for confidence interval is the point estimate plus or minus the critical value times the standard error. So for proportion, its point estimate is the sample proportion plus or minus the critical value of a proportion is the Z, okay? Times the standard error is the population proportion to bracket 1 minus P all over n, then the square root of everything, all right? Okay. This means that if you want to compute the Z value of the proportion yourself for the purpose of hypothesis testing, remember the computed critical value is the point estimate. Obviously, the point estimate is the sample proportion minus the population parameter, which is the population proportion, over the standard error. So the standard error is square root of P into bracket 1 minus P all over N. So that is how we compute the critical value of a proportion when you are doing hypothesis testing, because in every hypothesis testing, if you want to use the critical value approach, you need to compute the critical value, then compare it with the critical value that is given by a certain confidence interval. Then you would be able to accept the hypothesis or reject the hypothesis. So if you revisit the other videos on hypothesis testing, this will be clearer to you. But I'm just doing a revision here for the topics ahead. Now, in this particular topic, our focus rather is on doing confidence interval and hypothesis testing for two population parameters. Now, assuming that there are two groups, okay? So for instance, let's say I teach Bachelor of Commerce Management students, I teach them statistics. And let's say I teach Bachelor of Commerce Accounting students, I teach them statistics. Now let's assume that these two classes, they went to write a statistics quiz. And one class, let's say the average of the class is, let's say, 18 over 20. And the average of the other class is, let's say, 17 over 20. Obviously, once I'm able to get the average for the whole class, I can confidently tell that those who had the average of 18, they did better than the class that had an average of 17. But let's assume that I want to compare the statistics performance as in the average score of one class, let's say Bachelor of Commerce Accounting. Now, because they are College of Distance Education students, they have several centers across Ghana. We have several centers across Ghana. So probably there may be about 30 College of Distance Education centers across Ghana. Now, because I cannot use the entire population and I want to use a sample, when I sample and get an average of 18, it is just a point estimate. It doesn't mean that if I had the entire population, I would have gotten 18. All right. And again, the other class, if I pick a sample and the average marks they got was 17, it doesn't mean that if I had the entire population for the whole Ghana for Become Management, they would have gotten 17. So here is the case where I'm having a point estimate of 18 for become accounting because I picked a sample of them. And here is the point, I'm having a point estimate of 17 marks for become management because I picked a sample of them. Now, this brings us to the concept called independent samples. So when we talk about independent samples, they are samples selected from 2 or more populations in such a way that the occurrence in one sample has no influence on the probability of the occurrence of values in the other sample. In other words, it is when you are checking, so in plain language, it is when we are checking the differences in average for 2 independent samples. All right. So for instance, I said when I picked a sample of accounting students, not the entire population, but when I picked the sample mean was 18. And when I picked a sample of management students, their sample average was 17. Now, the difference between 18 and 17 is just 1, all right? But then the difference of 1 is for the sample. So the point estimate of a difference of 1 is for the sample. That's why we call it a point estimate of 1. So the difference between the average accounting and then the average of management, the difference of 1 mark is a point estimate because it is not for the entire population. Now, I can do a point estimate when standard deviations are known. I mean, population standard deviations are known. And I can do a point estimate when population standard deviations are unknown. Now here, remember, if we were talking about only one population, the point estimate would have been sample mean. But here, because we are talking about the difference between 2 populations, the point estimate will be the sample mean of the first population minus the sample mean of the second population. This will be the point estimate. Because we are talking about the difference between 2 populations, the point estimate will not be just the sample mean, but rather it will be the sample mean of the first population minus the sample mean of the second population. And then the standard error will be this. The standard error will be this. So technically, for a single population, that's what we've been doing up until now. Okay. The point estimate is the sample mean. But for 2 populations, the point estimate will be the sample mean of the first population minus the sample mean of the second population. When it comes to the standard error when population standard deviation is known. For a single population, the standard error will be the population standard deviation over square root of n. But for 2 populations, it will be the square root of the standard deviation of population 1 squared over the sample size of the first population or the first group plus the standard deviation of the second group squared divided by the sample size of the second group. All right, so this is how we find the standard error for 2 populations, is this one. If it's a single population, it's quite simple, but when it's 2 populations, this becomes the formula. All right. Now, this means that if I want to find the confidence interval, remember, every confidence interval is a point estimate. Plus or minus the critical value times the standard error, okay? Now, in this situation, remember that when it comes to two populations, its point estimate is the sample mean of the first population minus sample mean of the second population, all right? Plus or minus the critical value will be the Z, okay? The critical value will be the Z. And then the standard error obviously is this one here, square root of this one over N1 plus this one over N2. All right, so this is how we find a confidence interval for two population parameters when the standard deviation is known. All right, when the standard deviation is known. So these are our confidence levels. When we are doing confidence interval, it is two-tailed. So 80% confidence level goes with a Z of 1.28. 90% goes with a Z of 1.645. 95% goes with a Z of 1.96. And 99% goes with a Z value of 2.575. So let's look at the example. The objective is to estimate the difference in mean time spent. So please, in the question, once you hear difference in mean time spent, listen carefully. Difference in mean time spent. They are talking about two separate because of the word difference. Because of the word difference. So it means there are two groups. They are not, it's not just a one group. There are two groups, right? For male and female customers of the fitness center. So here, what it means is that we have the average for two separate groups, okay? And that will mean that we are estimating confidence interval for independent samples, right? So we will apply the formula. Now the question says, previous studies indicate that standard deviation is 11 minutes for males. So we can denote male as group 1. And then the standard deviation for female is 16 minutes. So these are the population standard deviations for group 1, which is male, and then group 2 is female. Develop a 95% confidence interval for the difference in mean times. So here, the question has given sample size for male to be 100, sample size for female to be 100, sample mean for male 34.5, for female is 42.4, and then we are testing at 95% confidence. So let's go back to our formula here. So per the question, the confidence interval will be mean of group 1 minus sample mean of group 1 minus sample mean of group 2 plus or minus the Z into bracket, the standard error, remember? Standard deviation squared of group 1 over sample size of group 1 plus standard deviation squared of group 2 over sample size of group 2. So in the question, the mean of group 1 is 34.5, that of group 2 is 42.4. Then obviously the Z is 1.96 because we are testing at 95% confidence. Then sample size for group 1 is 100. Sample size for group 2 is also 100. Then the question says the standard deviation for the male is 11 minutes, female is 16 minutes. So standard deviation for group 1 is 11. Standard deviation for group 2 is 16, I guess. Okay. So let's fix them into the formula. So the point estimate will be 34.5 minus 42.4 plus or minus the z is 1.96. Then the standard error will be the square root of 11 squared over 100, because standard deviation of group 1 is 11, so 11 squared per the formula over sample size of group 1, which is 100, plus standard deviation of group 2 is 16, so we have 16 squared because the standard deviation squared here over 100. Okay, so here will be minus 7.9. So minus 7.9 plus or minus the z value is 1.9. And then you punch everything in the bracket, which is the standard error, square root of everything here, you get 1.9416. So let's expand it. So we have minus 7.9 plus or minus 1.96 times this. Approximately, you are going to get 3.8056. Okay, 3.8056. When you expand it, it's going to be minus 7.9. Because here we have plus or minus, when you expand it, minus 7.9 minus 3.8056. That's the minus side. Then the plus side will be minus 7.9 plus 3.8056. So if you punch it, the plus side will be minus 4.0944. Then the minus side will be minus 11.7056. So the confidence interval for 95% will be minus 11.7056 to so 2 minus 4.0944. So this is how we compute the confidence interval for 2 independent samples when the population standard deviations are known. Now, if you want to compute the confidence interval when the population standard deviations are unknown, remember, we are going to use the t instead of the z. So when you are computing the confidence interval when the 2 population standard deviations are unknown, we are going to use the t critical value instead of the z. Now, the assumption we make is that the populations are normally distributed. The population have equal variances. That means that they have equal standard deviation, although it is unknown, all right? So here, let me add that confidence interval for the difference between 2 population means when the population standard deviations are unknown, but they are equal. Okay, so I want to talk about the confidence interval when the population standard deviations are unknown, but they are equal. So we don't know it, but we assume that they are equal. All right. That means that here we are going to use a t distribution instead of a z. Okay. And when that happens, because the population standard deviations are unknown, but they are equal, the question will give us the sample standard deviations. And that is what we are going to use. in place of the population standard deviation. All right. So the third assumption is that the samples are independent. So let's move on. So if that is the case, the confidence interval, the point estimate will be the sample mean of the first group. So this is the point estimate. The sample mean of the first group minus the sample mean of the second group plus or minus the t-value times the standard error. Now, in this case, everything here is the standard error. Everything here becomes the standard error, okay? Everything here becomes the standard error. So remember that whenever we are dealing with confidence intervals and then the population standard deviations are unknown, okay? The population standard deviations are unknown. What happens is that we are going to employ the sample standard deviations to compute the standard error using this formula. So the red circle or the red square I've made is the standard error. Everything there is the standard error. Now, in the formula, we can see a certain SP in the formula. So the SP in the formula is also expanded as this here. So the SP here in the formula is expanded as this formula. So write this formula down also. The SP here is expanded as this formula. So write this formula down also. All right. Then remember that when we are dealing with T values, okay, when we are dealing with T values, we have to read from the table. We do not have a standard T value like how we have standard Z values. When it comes to T values, we have to read from a table, okay? We have to read the T value from a table. And whenever we are reading a T value from a table, we will need a degree of freedom. Remember, if we were dealing with a single population parameter, the degree of freedom would have been n minus 1. But now, because we are dealing with two separate groups, it will be the group 1 n minus 1, and then plus the group 2, the sample size minus 1. The sample size of group 1 minus 1, and then the sample size of group 2 minus 1, that will be the degree of freedom. And this one is like mathematically saying sample size of group 1 plus sample size of group 2 minus 2. So this will be the degree of freedom that will be employed in reading the T table, okay? This will be the degree of freedom that will be employed in reading the T table. So in the confidence interval for two separate groups, when we don't know the population standard deviation, the formula becomes complex because the SP alone here is expanded as this. Then after that, you have to also again come and multiply it by the square root here of 1 over n1 plus 1 over n2. All right, so write these formulas down. Pause the video, write the formulas down, and let's move on. And the SP is called the pool standard deviation. So let's move on now. In a situation where the population standard deviations are unknown, but they are not equal. Let's listen carefully. So what we just spoke about was where the population standard deviations are unknown, but they are equal. Now, we can have a situation where the population standard deviations are unknown and they are not equal. If that happens, the formula will change a little bit. The formula is going to change a little bit. All right. Now, if they are unknown and they are not equal, okay? If they are unknown and they are not equal, obviously this one still remains the same. The point estimate will be x1 minus x2, the means, the sample means, plus or minus the critical value is the t. And then now the standard error becomes a little simpler, okay? So the standard error will not become complex like when they are unknown but equal. When they are unknown but equal, the sample error is this, the one circled here. But when they are unknown and not equal, I mean, when the population standard deviations are unknown and not equal, the standard error becomes simple. It is, the standard error becomes sample standard deviation of the first group squared over N1 plus sample standard deviation of the second group squared all over N2. This one is simpler. So remember, we can have a situation where the population standard deviations are unknown and equal. I've talked about it already. But this situation, the population standard deviations are unknown and they are not equal, right? And because we are using a T, we have to read from a table. And to read from the table, we need a degree of freedom. So in this instance, the degree of freedom formula becomes also cumbersome. So everything here is the degree of freedom formula when the population standard deviations are unknown and not equal, because we need a degree of freedom to compute the T, all right? So you can pause the video and write the degree of freedom formula down. Okay. So this will bring us to the first section on confidence interval for two population parameters. In the next video, I'm going to teach on hypothesis testing for two population parameters. So let's meet in the next video. Thank you.